I'll be talking about a modular and efficient past state system for Berkeley DB. This is work that I did while I was at Brandeis University with my advisor, Liuba Shrira, and this paper is also joint work with Barbara Liskov. So this is really about being able to add snapshots and point-in-time queries, which we call retrospection, to a database system, to Berkeley DB. So past states are useful. They can provide insights into your data. So you can do things like trend analysis. You can go back to previous points in time, analyze states of data and say, well, how did these query results change over time? You can do things like anomaly detection. You can say, well, over these points in time where there are values that looked unexpected. It's particularly useful for things like intrusion detection. You may not know that there was some bad actor who corrupted your data, but you were saving snapshots periodically. You find out later that this corruption happened or this illegal change happened. So then you go back and you compare, well, what were the values before and after that I think this intrusion happened? And also auditing, corporate governance and compliance. These things also require snapshots typically. So there's a lot of value that can be added to applications if a data store provides snapshots as a service. But saving consistent snapshots, consistent past states, is a challenging task, and not all data stores offer it. So Retro is a snapshot system for Berkeley DB. If you're not familiar, Berkeley DB is a transactional database. It now offers a SQL layer on top since it was purchased by Oracle a little while back. But it has the typical sort of database features that you would think of. But it's targeted at embedded systems, so it also has a C API underneath. The idea behind Retro is that we want to provide a sort of low overhead, non-disruptive snapshot system. That's sort of the primary goal. So if you have an existing query and update workload that you're sort of pounding your database with, and then you replace your Berkeley DB database with a Berkeley DB and Retro database, and you start saving snapshots, your existing workload won't take a huge hit. So we refer to this as being non-disruptive. So the other ideas are that Retro has a simple programming model. So in order to go back and access snapshots to take advantage of them, you don't have to do a lot of modifications to the way that you program your queries. So this means that, like, if you're using SQL, you're using the C API. It's very simple to make very few modifications to your code to access snapshots. And then finally, we want the integration of Retro into Berkeley DB itself to be very straightforward. So this means a simple design and a simple implementation for the person or people who have to do it. And it'll sort of become clear later why this is really nice, but basically it means that we are going to be able to take advantage of the good performance and good reliability features that you get out of your database and sort of lift them up into Retro in a very natural way. And so our approach is to use a layered design and extend existing database protocols and sort of turn them into Retro protocols. So there we go. The programming model is very simple. I'm showing how we extend the SQL API here. The extension to the C API is sort of similarly simple. You can begin a transaction. You can do any kind of updates or inserts that you want inside of it. And then if you want a snapshot, when you commit with a snapshot, and you can provide some name for it. Later, if you want to query that snapshot, you simply provide that name back to a select. And then when that query is performed by the system, the data that it'll be accessing is the data that existed at the time that transaction committed. So the features that we get out of a retro snapshot are basically, just to reiterate, it's transactionally consistent, it's global, so that means that you're getting all of your data and metadata in the database. So in particular, if you have indexes on tables, those are also included in the snapshot. Snapshots are named, so you declare a snapshot, you give it a name, you access it by that same name. And application declared, so that's when you commit and you say snapshot, and that's just it differentiates it from systems where maybe snapshots are only declared periodically by administrators. So here's an example. You have some application. It's running maybe in a web browser, submits a query to the current state, runs some kind of report. You want to compare it to some previous state. Maybe you suspected some intrusion. So you modify the query somehow in the report to be as of last year. And then the rest of the code inside the report runs in exactly the same way. It's just executed by the database as of some previous time. And so you get back some other value. And you wonder, oh, maybe this person changed their salary. So anyway. OK, so this is the architecture. The basic architecture of BDB looks very similar to any other database. We have some access methods. These are like B-tree or a hash table. And then underneath of that, we have the recovery component and the concurrency control component. In Berkeley DB, the concurrency control is sort of integrated inside the page cache. And so in retro, the snapshots are, in fact, at the page cache layer. And also, retro requires that we add another disk, essentially, if you want to get good performance. Retro data and metadata needs to be written to a separate disk. So that's the retro disk depicted here. But essentially, the modifications that we'll be making are written into are modified at the snapshot layer, which wraps the page cache and the concurrency control and recovery mechanisms. And there's also a small change at the database interface, which is just to add that as of and snapshot, commit with snapshot that you saw. So just briefly, why this design? If you try to add snapshots at a higher level, let's say at the logical level, say at the access methods, you would have to go in and perhaps add a new type of access method. This is, for example, the approach taken by MortalDB. This approach is very complicated, and it requires significant modifications to the data store. With low-level snapshots, for example, below the level of the database, so I sort of circled the disks here. This may also be in the file system, so it's not just at the disk or controller level. It may be at the file system level. But either way, it's below the level of the transactional storage manager, so it's expensive to get snapshots that obey transactional consistency. So it's sort of a Goldilocks argument that I'm presenting here. The paper goes into the related work in a little more detail, but basically what we're saying is that by integrating retro at the transactional storage manager level in the database, in Berkeley DB, we're able to efficiently take advantage of consistency and still get efficient snapshots. So our formal model for actually defining what is inside of a snapshot is the snapshot overwrite sequence, which we abbreviate as OWS because SAIL is not a very good abbreviation. So OWS of a history is simply a tagging of those operations which create the contents of a snapshot. So when you declare a snapshot, that's part of history, and it's also tagged by OWS. And when a page needs to be saved for a snapshot, that's also tagged by OWS. So OWS, it tells us which pages need to be saved during runtime for snapshots. When we perform a retrospective query, when we perform a point-in-time query, we can use this OWS model to tell us which pages are part of that query. And after a crash, during recovery, we can also use the OWS model to tell us which pages need to be recovered. So this is an example history. We declared a snapshot. We've updated a page a couple times, declared another snapshot, and updated another page, and then page P again. The pages in here, or the pages and operations in here which are tagged, are basically all of them except for this second update to P. And the reason for that is because it is not the first update to P since a snapshot was declared. Okay, and the reason for that, the intuition behind that is that we need to save the pre-state of the first update to a page since a snapshot was declared, because that is that pre-state is the page that was in the current state when you declared the snapshot. And if we just sort of visualize these pages over here to your right, and we think about the OWS as defining which pages need to be accessed for retrospection, S1 is going to be looking at maybe there's another page R in the current state, so it'll look at that page. And then it'll look at the first copy of P and the only copy of Q that we have here. S2, meanwhile, will be looking at, again, R in the current state, the only copy of Q that we have, but it'll look at the second copy of P, because that was the copy that was saved after S2 was declared. So saved after is a data structure that actually implements part of the OWS. So the OWS is a formal model, but we have metadata structures, both in memory and durable, which actually sort of implement it so that you can use it during runtime. So it's a durable table that tracks the latest snapshot after which a page was saved. So during retrospection, you need to read it in order to find out whether or not you have to go and get, in this case, during retrospection, you would need to see if you get a pre-state. That would be one of the pages that's either purple or blue here, or get a current state page. That's one of the white pages. And when updates commit, you have to go and modify saved after if you save a pre-state, because then saved after, of course, has changed. That's like you're making a new tag in OWS, so then saved after is modified. So saved after, of course, then can be costly because this is a shared data structure which is both read and written. So we have a cache which accelerates saved after by actually scribbling this tag inside pages in the page cache. And there's some details about this in the paper. I'm just going to skip over this, I think. This is just sort of basically showing how page sharing works. But I think we're all pretty familiar with copy on write. I can come back to that if there are some questions. So the recovery extension is basically saying that, like the database, snapshots are written asynchronously, and this is how we achieve non-disruptiveness. So instead of writing a brand new recovery protocol, Retro extends existing database recovery protocol. So we actually piggyback on the write-ahead log work that the database already does, and leverage the recovery protocol that the database executes after a crash in order to reconstruct pre-states and restore them during recovery. So Retro will, during database recovery, Retro will actually monitor the pre-states that are created in the page cache as the database applies redo records during its own recovery. So basically the database during recovery will read a page from disk and apply redo records to it. Retro will monitor those pre-states and its own saved after data structure and say, oh, do I need this pre-state? And if so, it will save it. And this is basically the same procedure that it does during normal runtime. Now, we have to enforce an invariant here. The database will throw away its own recovery information periodically. And it does this because it needs to keep the log short, because it's flushing its own data to disk. But retro has to be able to make sure that the redo records that get applied to pages produce the correct pre-states that it needs. So we have our own invariant that we enforce on the database called the write-ahead snapshot invariant, which says, well, you can't throw away your own recovery information until we've made our snapshots durable. So this is called the WAS invariant. So sort of gluing this together, retro is implemented as a set of callbacks inside of Berkeley DB. It's about 250 lines of actual modified Berkeley DB source code, and about 500 lines inside of the 5,000 lines, sorry, of sort of code inside the snapshot layer. The snapshot layer itself is implemented sort of as Berkeley DB code, so we leverage transactional and recoverable data structures for saved after and some of the other metadata structures, which makes them easy to recover. And then we have to take care that retro itself is thread safe, because BDB is, of course, a multi-threaded data store. So I'll quickly go through some experimental results. The database, so let's see, I'll talk about this non-disruptiveness experiment here quickly. What we did for non-disruptiveness is we performed a sequence of random updates with and without retro. So the without retro experiment, we actually just completely disabled retro. And this is a micro benchmark that performs just updates. And what we did is we compared the throughput of performing updates, saving snapshots after every single transaction, to updates saving no snapshots at all. And what we found is that the throughput impact of saving snapshots was only about 4%. So actually, saving snapshots has a very low impact on the update throughput. And the main impact actually comes from lengthening the checkpoint time. The CPU overhead is actually somewhat high. We did a conservative experiment with measuring CPU overhead, where we did random queries in a completely in-memory database. Both the retrospection query was completely in memory, and a random database query that was completely in memory. We found that there was about a 50% overhead that was sort of in line with previous results, such as the Shaull MT results, for adding sort of an extra trip through the database buffer cache to cycle back through and figure out which snapshot pages you need to locate. And the final experiment that we looked at was looking at the cost of I/O during retrospection. This experiment is a little subtle, so I'll leave some of the details to the paper, but the sort of high-level bit to take away from this, a takeaway point, is that while it is more expensive to perform a retrospective query because of the cost of declustering your I/O, remember this is a copy-on-write system, so pages are not in order, it is still only about maybe 1.7 times more expensive, and you're getting it at the cost of a very low impact system. So I'm definitely over time now, so I'll leave it at that, but I'll take questions. I would be happy to talk about related work.
Yes, I know. Okay. So you may know that there was a lot of research on this in the late 1980s, including my own PhD thesis at Berkeley, and Richard Snodgrass on TSQL and a bunch of others. This is definitely well-trodden territory. And so one thing I think that would be valuable would be to put this into some perspective in terms of, how is this novel? How is this, advance of the state of the art in terms of what's been done before? Because it seems to me that a lot of this has really already been done.
So I think that what makes this a novel approach is that it's integrating at a different system layer, and it's actually so if you think about how to integrate a logical, so most approaches that you're talking about are logical layer approaches where you're actually creating new high-level data access methods, right? And so this approach is saying, well, we're going to create a brand new system layer that you can insert into the database near the page cache, and you'll get all the same features that you get above that layer in the database, but you'll actually be able to save snapshots of those same data structures. So I think in that sense, it's an entirely new approach to saving snapshots that is very different from most of those previous systems. Now, there are some current sort of industrial approaches which save snapshots at the page level like that, including SQL Server, but their organization of how they save those pages in sparse files is very different than the way we organize our pages and our metadata. And the way that we do that is more efficient.
Okay. I think that's debatable. We can take this offline.
Sure, I'd be happy to.